We're starting with step 4A. We're going to estimate the curve number. In order to do this, we first classify the hydrologic soil group. Soil groups are classified qualitatively and quantitatively by minimum infiltration rate. A lower value will mean less water is absorbed, resulting in more surface flow and a more conservative value to use overall. This is group A, B, C, and D, and I've shown the difference in infiltration, which is going to result in the difference in Q, or our runoff depth. Group A soils, more specifically, have a low runoff potential and a high infiltration rate, even when thoroughly wetted, and they consist chiefly of deep, well to excessively well-drained sands or gravels. Group B soils have a moderate infiltration rate when thoroughly wetted, consisting chiefly of moderately deep to deep and moderately well to well-drained soils with moderately fine to moderately coarse texture. Group C consists of soils that have slow infiltration rates when thoroughly wetted, consisting chiefly of soils with a layer that impedes downward movement of water or soils with moderately fine to fine texture. And finally, Group D, which we will choose conservatively, is soils that have high runoff potential and a very slow infiltration rate when thoroughly wetted, consisted chiefly of clay soils with high swelling potential, soils with a permanent high water table, or soils with a clay pan or clay layer at or near the surface, and shallow soils over a nearly impervious material. After determining the hydrologic soil group, we can use that to estimate our curve number based on tables for various land use types. And I will link those tables below. So helpful information and or tools in estimating the curve number come from the site media, especially during the rainy season when this information is the most relevant. So not only take a look at Google Earth images, but review your site media in depth and do your best to describe the surface condition in terms of these curve number tables. And at this point, you could choose a conservative curve number, keeping in mind that this can be tweaked over time. Some examples from the tables I've pulled out for you are curve number for natural desert being 63 to 88 is the range, poor brush 48 to 83, and fair woods 45 to 83, and this range comes from the hydrologic soil group. Then step 4B is to estimate the runoff coefficient, or C for the rational method. In order to calculate a composite runoff coefficient, we can weight various coefficients by area. We have the sum of individual coefficients times their area over the sum of the areas is going to be equal to our C. And each individual CI we can also determine from various portions of the watershed by using Google Earth and site media. And these coefficients are tabulated online for various land use and cover situations, very similar to the curve number method. Finally, we'll move on to step 5A, which is going to be calculating Q for the SCS curve number method. For the curve number method, Q is in inches and it is our runoff depth. We have our governing equation Q equals P minus IA squared over P minus IA plus S, where we can calculate S, our storage, based on the curve number, as 1,000 over Cn minus 10. And next, we can calculate initial abstraction, or the amount of rainfall that is initially absorbed into the ground during a storm event. And based on storage, IA is about equal to 0.2 times S. And finally, we can calculate our cumulative rainfall excess, or our runoff Q, with the addition of the variable P, which we input as our cumulative total rainfall from the storm. All of these values should be in inches, which we can later convert to centimeters or meters to be consistent with our units. Now we need to note that Q is our runoff, so this will add to our base flow depth in order to create our peak discharge. So I've drawn a little diagram for you. On land, this will be our runoff when we have a groundwater flow. That will be our Q. But through the stream, we have our base flow and our runoff above the river bed. So we need a few more equations. And these are kind of scary looking equations, but a lot of these variables we already know. So we need to calculate QP, our peak discharge. QP is equal to QU times A times Q, where Q we've already calculated in inches. AM is our basin area, which we measure in this equation in square miles. And QU is going to be a long empirical equation that is 10 to the C0 plus C1 log T plus C2 log T squared. Coefficients C0, C1, and C2 are the TR55 coefficients, and they're tabulated based on rainfall type, which is a function of IA over P. And I'll add another table for reading that value for you. So those we just read off of a table based on our rainfall type. And the last bit we need to get is our time of concentration in hours, TC. This is how long it takes for runoff to flow from the furthest point of the watershed to our point of interest. This can be estimated with the SES lag formula. And the lag formula is, once again, another empirical equation that is 0.000526 times L to the 0.8 times 1,000 over a curved number minus 9 to the 0.7 times S to the negative 1/2. And that's going to be in hours. And then we can just calculate our TC, our time of concentration, as 5/3 of our TL. Now, the two new variables here are S, our slope, which is going to be in a percentage value, and L, which is going to be the length of the watershed. And note that you can take S as the average slope of the watershed. Finally, we have our TC. We can plug that back into the equation for QU, which we can plug into the equation for QP to get our peak discharge in cubic feet per second. Step 5B is to calculate our peak flow using the rational method, and we'll call that QR. And this is a much shorter process. This is why people like to use the rational method, but unfortunately for those small areas, it doesn't give as good of results. Our rational method equation is Q equals CIA, where C is our weighted coefficient, A is the area of our watershed, and I is the rainfall intensity in inches per hour that we get from our storm characteristics back in step 2. This gives us a peak discharge rate and CFS. In the next lecture, I will go through how to actually model this flow through our specific channel and calculate a depth